Today we're going to look at some totalizer traps to watch out for. They're just as relevant if you're totalizing tons on a conveyor belt or water through a pipeline. So in our scenario, a new pipeline has been installed. A flow meter has been installed as shown below. You need to keep track of how much water passes from A to B. The simplest implementation is to have a 1-second timer. When the timer is done, add the current flow in liters per second to a totalizer value. So here our timer is counting up to 1,000 milliseconds. When that time is done, we add our flow of 1,000 liters to our flow totalizer. So far so good, right? Right? If we look at the value in the accumulator each time the counter is done, you can see that often the done bit comes on after 10 milliseconds or so has passed. So here, 18 milliseconds has passed, 16 milliseconds has passed. Now, this might not seem like much, but an extra 10 milliseconds every second over an hour results in 36 less seconds counted every hour. That results in 36,000 liters being missed per hour. The remedy is instead to monitor the clock of the PLC, and every time the second changes, trigger a pulse and add to your totalizer. Here we compare the PLC's second counter to what the second was the previous scan. If it is different, trigger a second pulse and move the current second into the second previous scan variable. Every second, add the flow to the totalizer. Both of the previous totalizers were DINTs, which are double integer data types. A DINT has a maximum size of 2 to the 31, which is 2.147 billion. That's plenty of space. If flow is consistently at 1,000 liters a second, that turns out to be 86 megaliters a day. Within 25 days, the totalizer will overflow. You will add 1,000 to 2.14 billion, and the result will be minus 2.14 billion. Fed up, you decide to change the data type of the totalizer to a real, which is a floating point data type. A real can represent numbers up to 3.4 times 10 to the 38. That's huge, you'll never fill that up. Every new second you add the flow to the new totalizer. The flow isn't always exactly 1,000 liters a second. Sometimes it's 1,001 liters a second or any number nearby. So if we change this to 1,001 liters a second, every time the second pulse happens, we add 1,001 to the total. But you notice something magical happens when the total grows above 16 million. So if we set it to 16,777,216, now every second we're adding 1,000 onto the totalizer, but not 1,001, we're just adding 1,000. So where is the 1 going? To find out, we need to deep dive into floating point numbers. In Allen Bradley PLCs, the real data type uses 32 bits to store an approximation of a floating point number. The 32 bits are broken up into 3 sections: the sign, the exponent, and the mantissa. In order to represent a floating point number, the following formula is applied. -1 to the power of s times 1 times the mantissa times 2 to the exponent minus 127. The parts of the floating point number are separated below to demonstrate how floating point numbers work. The sign determines if the number is negative or positive. The exponent determines the base number to which the mantissa is added. The mantissa represents the precision bits of the number. If you set the exponent to 128 and the mantissa to 0, the result is 2.0. If you set the mantissa to 8,388,607, the result is 3.999. So when the exponent is 128, there are 8.3 million numbers between 2 and 4. If we increase the exponent to 151, so we'll set the mantissa back to 0, and increase the exponent to 151, the result is 16,777,216. Now if we set the mantissa to 8,388,607, the number is 33,554,430. Now there are only 8.3 million numbers representable between 16.8 million and 33.6 million. Every integer cannot be represented. So 16,770,216 plus 1 is equal to the same number. This is known as floating point absorption. Often, the best alternative isn't to sum the instantaneous flow rate, but instead to configure the flow meter to pulse every 1,000 liters. That way, you will only have to count individual pulses and you'll be able to deal with integer values. It is also the most accurate alternative, as the flow meter is the source of truth with no scaling or signal drift to contend with. Unfortunately, not all flow meters have a pulse output, or you may need to totalize a calculated quantity that is related to the flow rate, so you still need to sum messy values. There are many strategies you can use to combat floating point absorption. One option is to use an intermediate totalizer to totalize small amounts and add it to the larger totalizer. Compare the larger totalizer before and after each addition and remove the amount added to the larger totalizer from the smaller totalizer. Here I have a manual toggle instead of the second pulse so that we can step through each step of the algorithm and see how it works. So initially, I'm going to add the flow of 1001 liters per second to an intermediate totalizer, and I'm also going to copy the totalizer value into a total before addition variable. So I'll toggle that pulse on and off, and here we can see that the intermediate totalizer is now 1001 liters. Now the second step is to add the intermediate to the total value, and then to subtract from the intermediate the change in the total. So the total after the intermediate has been added to it from the total before the addition. So if I toggle this pulse, we can see that the total is now equal to 1001 and the intermediate is equal to 0. So the whole of the intermediate totalizer has been moved into the total totalizer. Now, if we do that again, but what we'll do is we'll increase the totalizer to 16,777,216. So this time, we're again going to add the flow this second to the intermediate totalizer. Now we're going to attempt to add the intermediate to the total. And when we do that, 1,000 was added to the total. And in the intermediate, we have the leftover 1 that would have been absorbed. Now, if we go through the process again, now we have 1,002 in the intermediate. And if we attempt to add that to the total, you can see that 1,002 was added, so our intermediate is now back to 0. What we can also do is increase the totalizer value, so we'll multiply it by 10. And we'll attempt to do the same thing. So our intermediate value is once again equal to 1,001. And if we attempt to add that, what we get here is the intermediate was added to the total, but because the intermediate couldn't be exactly added to the total, it was rounded up. And so now in the intermediate, we have a value of -7, which is good. So the intermediate is keeping track of any numbers that are absorbed or not able to be added into the total in a neat way. And that way we don't lose liters. Yeah. If we're dealing with particularly big numbers, say, or totalizing gigaliters, well, instead of just adding the flow to the intermediate, what we can do is we can add the flow divided by 1,000, and that way we'll be summing kiloliters rather than liters. And before I apply that change, what I'll do as well is I'll reset this intermediate value, and I'll also I'll change this back to a second pulse and remove the one shot. I'll do the same down here, just so I don't manually have to toggle it each time. I'll apply the change. Now, every second, this code will execute, and what you can see it doing, so every second it's attempting to add 1.001 to the totalizer, and it keeps getting added to the intermediate because it's too small to be absorbed, and then it jumps to -7.9 as the intermediate value grows large enough to be rounded up and added into the actual total. So by setting up an intermediate totalizer, you're able to keep track of these smaller parts of the number which would otherwise be absorbed. And floating point numbers have a good resolution down at the lower numbers. So this dividing by 1,000, you're still able to accurately keep track of the numbers. Another helpful strategy is to regularly reset your totalizers. Realize that you cannot totalize a value forever. A PLC was not designed to store an ever-increasing total. Use an external database for that. Store totals in a PLC as long as you need to, but realize that you will need a strategy to reset the totals to 0 periodically. Whether it be weekly, monthly, yearly, or when the number grows to a certain size, you need to design how your totals will be reset. As a recap, so the three traps were: trap 1, time adrift. The remedy was to detect second changes rather than relying on a 1-second timer. The second trap was totalizer overflow. The remedy is be careful about what data type you select your totalizer to be. The trap 3 was floating point absorption. The remedy is to use an intermediate totalizer. And remember to design how your totals will be reset.